Welcome to another edition of the Chemistry Podcast. This one will review the progression of the atomic models from the early 1800s to how we see it today. A couple questions begin this conversation. One is, as you find new information, how does it support or weaken a model? And then how do these new models come up as a result of newfound information? In 1803, it was John Dalton who was able to define an atom as that simplest unit of an element. The story began. Towards the end of that particular century, Thomson was able to use what is considered a TV tube. We don't see a whole lot of these anymore. However, just imagine you have this ray. This is just a gas tube, and with the electrical current on, let's go back, we can take a magnet to that gas and see that it actually is attracted to the magnet. So it was discovered that the material inside the gas tube must contain something that is different from what we've already known in the past. And this led to literally the atomic model, Thomson's model, as what is now known as the plum pudding model, because plum pudding is sort of a dessert that is eaten in England. And if you could imagine, these are the plums, little electrons here, inside the pudding. And so what you were seeing there with the magnet was the negatively charged particles that were attracted to the magnet, and it was thus discovered that, hey, we now know that there are these negatively charged particles within the atom. Thomson was so struck by this discovery that, quote unquote, he responded with, "Could anything at first sight seem more impractical than a body," referring to the electrons, "which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen?" New questions came up as a result. Since matter has been found to be electrically neutral, then, and we have these electrons, then where are these positive charges in the atom? And secondly, if an electron is really so small in mass, what is accounting for the other part of the atom? And so, as you can see, discoveries just give rise to new questions, and this is the process of science. In 1910, Ernest Rutherford was able to conduct an experiment which gave rise to new information. As you can see, we can take sensitive mouse here, bear with me. As you can see, we can take the alpha beam. So an alpha particle is actually a helium atom without its electrons. So think of this alpha beam, this beam of alpha particles, as a positive set of particles that are basically pointed at this gold foil. So you shoot this beam towards a very thin piece of gold, and what was discovered is some of these particles deflected and bounced off the front. However, unexpectedly, some of these particles, remember these are actual particles of mass, some of these particles actually went through the gold foil and were discovered at various degrees, various angles from the entry point. And so here is a cross section on a more atomic level of what happens. So this is alpha, this Greek letter here. So the beams are all coming from this side here, on the bottom here. Some of them are going straight through, so that would be the same as these particles that go straight through the foil without deflecting, whereas some particles were going through the foil and coming out at an angle. And finally, some of these are actually not coming through the foil at all. What can we deduce from this? And so this actually gave us a conclusion that, hey, the center is fairly positive. And the center is fairly positive. We know this with the electrons must be somewhere on the outside. And if you go back and look at the model, you'll see it makes sense, because if you have alpha particles which are positive and they're going towards the positive center and actually deflecting, or you could say repelling off, then that makes sense that the center is positive. And if you have also alpha particles that are going straight through certain spaces where there are no nuclei particles, then that makes sense that you have all this empty space here outside of the small dense nucleus. So now we know that the protons are the center of the atom. The rest of the atom was, however, still a mystery, mass-wise. This takes us to 1932. James Chadwick discovered that, hey, the rest of the mass is neutrons. And we now know that neutrons are equal in mass to protons, and we also know that neutrons have no charge. That was discovered through his experiments. Then we delve deeper into the puzzle. The question is, okay, if the electrons are not in the nucleus, where are they outside of the nucleus? This leads us to Niels Bohr's experiment. And this is roughly 1913. I guess I should make a little notation there. Oops. We'll get this right in a minute. I don't have this in pen mode yet. Roughly 1913. And this experiment is pretty interesting, because what he actually did was he was able to excite atoms to a point where when something became heated, as it was released, he could discover that, hey, the energy from electrons would represent the energy levels of the actual atom. And so we can now realize that electrons exist, yes, outside of the nucleus, and we also know that the electrons can exist in specific energies levels around the nucleus. But once again, as with most models, they're never perfect, and new questions arise as a result of previous experiments. So these electrons, if they're negatively charged, and the protons are positive, right? And last time I checked, electrons are attracted to protons. Opposites attract. So why don't these electrons go crashing into the nucleus? And this brings us to the quantum model. This is roughly around 1927. So we can make a little notation here. We know that electrons don't orbit around the atom in these nice circular planetary-like paths. There are really regions around the nucleus, very specific distances, at specific distances from the nucleus, that electrons are most stable at. We call these areas orbitals. Come on. And this concludes the Atomic Models podcast. As you can see, the atomic model progresses, it changes as a result of new discoveries.